Okay, so what do I want to get into now? The next part that I want to cover is a little slideshow presentation on foundational concepts in C# programming. So I'm putting a link to the same slideshow that I'm showing you right here. And I'm going to go ahead and make this full screen as well. So give me a little bit of thumbs up if you can see the slideshow. What I want to talk about is a bunch of concepts that are going to be really essential as we move forward and start working with objects inside of C#. And specifically, I like to start out with a general question that I give everybody in class. When I was teaching this on campus, I would start out the class by saying, well, what is a computer program? And I would get everybody to share their ideas about a computer program is this, a computer program is this other thing. And then I would wind up sharing my own definition of what is a computer program. I like to say it like this. A computer program is a set of instructions for manipulating information. It's a set of instructions for manipulating information. And then I would go and I would get everybody in the class to repeat it. In fact, let's try that. Let's see how that works online. Turn on your microphones, everybody. Turn on your microphones. And on the count of 3, we're going to say this line together. Okay. So on the count of 3, 1, 2, 3. A computer program is a set of instructions for manipulating information. So now at least you know why I don't do it online. That is okay. You can mute yourself. Mute yourself. That is a perfect meme there that you've got. Um, but on campus, I would love doing this kind of a thing because of two things. Number one, I really want to drill in the idea of this definition. But number two, it really freaks out people walking outside the hall of the classroom when they hear everybody chanting this together. I like to mess with people's minds a little bit. But I like this definition because it has two essential components, and you can probably guess what they are because they're already in a blue color there. There's the whole idea of information. Information is central to computer software. A computer program is all about information. And the other idea is the instructions that are used to manipulate information. So a computer program is a set of instructions for manipulating information. If you keep that definition in mind as you move forward through all of the stuff that you do with C# and as you move forward with learning classes, you're going to see how all of this stuff starts to fit together. One of the first questions that we have to ask after we see this definition is, what do we mean by information? What do we mean by information? Well, information comes in general terms in about 3 different ways. Information will be either textual information, or it will be numeric information, Or it might wind up being something that is uh, more conceptual in nature. So rather than textual or numeric, you might have a concept. So for example, if I show you something like this, that's not really a letter in the same way that this is not really a letter, but those are concepts. X or no, check mark, yes, or you could even think in terms of the Boolean types you've been exposed to, false, true. So those ideas. So you can have textual information in general. You can have numeric information. You can have conceptual information. And when we talk about information, every time we talk about it, in the background, there's another story going on. And that is understanding information in terms of variables, values, and data types. Inside of our computer program, when we work with information, we're using these three concepts, and the data type becomes the foundation for understanding how variables and values work together. So a value is the actual piece of information. That's the thing that we are concerned about. That's the thing we care about. The variable acts like a container, a way to reference that information. And the data type describes the information, how much memory is being used, how to interpret the ones and the zeros, the bits and the bytes that are in memory. Because inside of RAM, random access memory on your computer, all the information is being stored in a binary format, a whole bunch of ones and zeros, one after the other. And when we're talking about a variable, we're talking about some spot amongst all that RAM, those ones and zeros, some place where we have a whole bunch of ones and zeros, a whole bunch of bits, bytes of information. And that block of memory is the raw information, but it's only in ones and zeros. We need to understand it in a more meaningful way. What I often like to do is think of that information that's in RAM as being like a block of memory. So I draw a box, and inside of the box is the actual data. But on the edges of the box is metadata, stuff that helps to describe the data. So you have the name that you're using to refer to this variable, your variable name. And that variable name actually is associated with a memory address for where this data is located. We don't type in actual memory addresses. We use these easier to understand names in our higher level programming languages like C#. And then we also have this notion of the data type. I have a whole bunch of ones and zeros here, but what do those ones and zeros mean? That's what the data type information is talking about. What does it mean? And the scope, well, the scope is about who has access to this information. Who can see it? Because information is important. We want to guard it. So there's all this metadata, all this stuff that's surrounding the ones and zeros inside of our computer memory. And having a way to visualize it can be really helpful. It's especially helpful because in the language of C#, there are two general classifications you can have for all of the data types that are possible. All of the data types inside of C# will be either a value type or a reference type. Now, a value type is the kind of data type we see when we're dealing with information in its simplest form. That is, in its smallest, most meaningful form, things like integers, doubles, Boolean, char, float. That kind of information is what's called a value type. And all that simply means is that inside the box is where you'll see the actual value. So if I had a variable called answer and I had the value 42 and stored inside of it, it would be at some memory address, maybe A0B420. And this variable, maybe it's a local variable, it's only accessible by the main method. So that would be an example of a value type. And that works good for the primitive, the most simplistic kind of information, because we can know precisely how much memory it takes up. I know that an integer takes up 4 bytes or 32 bits of memory, 32 ones and zeros. So that works really well for value types. But every once in a while, I run into a kind of information that I don't know exactly how big it will be. Now, all of the built-in data types of C# are value types except for one. One of them is a reference type, and that is the string data type. The reason that it's a reference type is because when we're thinking about textual information, and we have to ask ourselves the question, how much memory do I need to store this textual information? For a string, it can really vary. I could have an empty string or a string of just a few characters, or I could have like the whole Bible inside of a string. And each of those are going to take up different amounts of memory. Well, if we're going to have a variable refer to that memory, how do I know how much to set aside? Well, it gets a little bit tricky if I want to do it just within the box. So I instead use 2 boxes. A reference type variable, such as the string name, is divided into 2 boxes by taking that name variable and the thing that you actually store inside of it is another memory address. And that memory address is where this actual value resides. So it, as a string, references where the data really is. And that reference type gives us that flexibility to have this second box grow or shrink as is needed, so we don't waste information, we don't waste memory trying to store the information, and we always know that we'll have enough memory to store the information because it can be as big as we want it to be. For the built-in data types, the only reference type is string. Where else do we use reference types? That is with classes. So Ping, you're exactly right. A class or an object is also done with reference types. Every time you declare a class, what you're actually doing is you're declaring a data type that acts as a reference type for information. So with reference types, it's going to be 2 boxes. And if we have a class called die, for example, and I want to create my variable fuzzy red die, and I have a null value inside of there, null is equivalent to a memory address of 0. Oh my goodness, I'm right up against the wire. That's okay. I've only got a few more slides. So that memory address of 0 is a null address. And if you ever have an error that says null reference, that means that you have a memory address that doesn't exist. All memory addresses start at 1. So your RAM starts at memory address 1 and goes up. So memory address 0 doesn't exist. When we have a reference type to actually have a value, we need to have an instance of it. So if I said fuzzy red dye is a new dye, then what winds up happening is that my fuzzy red dye references a memory address to D20E4125, where my actual information is stored. So that is the idea for a reference type. If you keep those two ideas in mind, that's going to go a long ways towards helping you understand what's really going on. Now, for all of the variables, values, and data types, there are 5 rules that always have to be kept in mind. First of all, any value that you store in a variable has to have a matching data type to the variable. So they have to be compatible. I'll talk a little bit more about that in another class. Variables also have to be declared before you can use them. You have to have the box there before you can put stuff into it. And once you declare your variable and you say, this is the box and this is how big it is, you can only do that once. You can't go and call 2 boxes by the same name within the same scope, or else the computer will get confused and won't know which one you're talking about. The other thing about these boxes is these variables can only hold one value at any given time. And each of our variables have to have a distinct name so we can tell them apart from each other. So those are the rules for variables, values, and data types. That is the basic foundation that we would wind up having for working with and understanding all of the basics of foundational concepts. When we come back in Monday's class, I'm going to continue on with another one. In fact, I'm going to want you, as part of your homework this weekend, is preview Monday's slideshow so that you can come and be ready and familiar with it, and we'll be able to run through it nice and quick. So here is a slideshow about objects. I'll put the link to that inside the chat, and I'll dive into my presentation. Okay, so when we're talking about classes, we're talking about the whole ability to create a new data type. And when we have a new data type, that's basically a blueprint to describe what the thing looks like and how it behaves. So, for example, if I wanted to model or have within my program the notion of a car, I might be interested in tracking information such as the color of the car, the VIN number, the make, the model, things like that. I may want to be able to do certain things with the car. I may want to repaint it a different color, or I may want to be able to have the car drive or move or do things like that. And the class acts as the blueprint to say this is what it looks like and this is how it works. But a class is distinct from the object itself. An object is an actual instance of a class. That's where you go and you take that blueprint and you build a real thing. In the same way, that if you had a physical blueprint for a car and you unrolled it and laid it down on the floor, sat down on that blueprint, you can go vroom, vroom all you want, but it's not going to get you anywhere. The blueprint is just a blueprint. It's only until you take it into a factory and construct a car, which is why we wind up calling the thing that helps to put the initial values on the properties of your class a constructor. It's only when you construct a car that you have the actual instance of that thing. Or let's look at another example. Here I have a class that represents a die that you would use in some game where you want to get some random numbers. And this particular die has a variable number of sides. It can have anywhere from 4 to 20 sides on this particular die. It's got two constructors. It's got a parameterless constructor. So I'll just go and I'll annotate the different pieces on here. So this here is a parameterless constructor. It's called parameterless because it doesn't have any parameters on it. And this parameterless constructor is chained to another constructor that takes an integer. And what we're doing is we're basically going and we're saying if they create a die and they don't tell us anything about how big it is, we will go and call this other constructor and pass in the value 6 for the number of sides on that die. So the default is going to be a 6-sided die. Otherwise, they'll tell us how many sides there are. Yeah, this is that's probably a common place where you wind up seeing multi-sided die in games like that. Notice when you create a die with a certain number of sides, I've got a little bit of validation in this constructor where if it's got an invalid number of sides, I'm going to throw an exception. Now, I don't know who created this die, and I really don't care who created it. It might have been a web application. It might have been a console application. It might have even been a totally other computer program that decided to go and interact and create this die. So I can't make any assumptions about how I would tell them or get a better value for the sides. The only thing I can do, and the only thing I should do, is say, no, I can't create a die with sides less than 4 or sides greater than 20. I throw an exception and I let whoever was creating my instance of the die class to decide what they want to do to recover from that. Now, when I create the die, one of the things that happens is that I've got a local variable called sides, which is this one right here. That variable has what's called a local scope. So parameters and local variables have a local scope. That means they only exist within that method. but to distinguish it from my property that was a member of the die class, I would refer to this dot sides. If they had the same capitalization on the S, then I would need to have the keyword this. But I want you to note that this property here, that item there is referring to that particular property. The this isn't necessary in the sample code that I have here, but I just kind of wanted to point out a little bit that when I talk about this, I'm actually talking about this specific instance. So it's really talking about this instance of the die class. So if I have different die, I'm not going to be talking about if I have a fuzzy red die and a solid blue die, and I'm creating my solid blue die. When I'm referring to the sides, it's the sides for that solid blue die that I'm instantiating. So that's a little bit of a thing that's kind of hard to describe without some pictures, but essentially that's what my code is doing, referring to the instance of the die class. Then I'm calling the roll method, and in the roll method, I'm going and randomly selecting one of the sides of the die. Now, here's something also that's really interesting, and that is this is one of the very few cases where you might want to have a static. So it's appropriate to have the random number generator as a static field because it can be shared by all of the different instances of the die class. They can all use the same random number generator. And so that makes sense to keep that static. Don't give each of them their own random number generator. Go ahead and let them share one, and that'll help keep things really random if they do that. So this has got a whole bunch of characteristics and aspects of some nice object-oriented programming. Notice also, I'll throw in another little bit of interesting point. Notice how I've had public int face value and public int sides, but I've had the private sets. The setter on each of these properties is private because I'm saying that you do not directly change the number of sides in the die, and you cannot directly change what side of the die is showing up on the top. The only way to change what the face value is, which side of the die is showing up on the top, is to roll the die. So I've built a class here that is following some good object-oriented principles in terms of hiding and protecting information and existing for a kind of a single purpose. Any questions or comments about the die class here? We are going to take some time to go and code this. Not tonight, but we will be getting into coding this one. Here's another example. There is a class called fraction, which represents, as you might guess, the idea of a number that has a numerator and a denominator. Inside the fraction class, I might have two properties, one for the numerator, one for the denominator. And I might have the constructor that says, in order to create a fraction, you have to give me those two values, the numerator and the denominator. And then I might have a method on there that allows me with this fraction to generate the reciprocal. That is to flip the numerator and denominator. So I do that by returning a new fraction where I substitute the denominator in for the numerator and my fraction's numerator in for the denominator. That'll give me another fraction. And I could also wind up putting other methods on this, such as a method to express it as a string, and maybe a method to express the value as a double to allow me to do some math on it. So that's another example that we're going to wind up working with. And we'll build out some enhancements on this. We're going to add in some stuff to fix the sign. We're going to have some stuff to say, is it a proper fraction? We're going to add in implementations for arithmetic operators and that as well. So that's one of the examples that we're going to wind up going through. Here's another good class. This one represents an angle. So the angle in this case would be in degrees, and we can express it in a string using the degree symbol, which is that Unicode character. That, by the way, is a single char. That's a single character, Unicode character for the degree symbol. You can see where I got it from. And an angle, although it is in degrees, could also be expressed as radians or grads, and we can do some conversions of stuff. And we could then maybe discover some other things and add in another property to go and determine what the angle type is, where we can say this is an acute angle, a right angle, an obtuse, or a straight, or a reflex, or full rotation, or maybe something undefined. Here's another example of doing object-oriented programming. And this one brings in a concept known as composition. So here's where we would have a class representing a deck of cards and another class entirely representing an individual playing card, where we could have enumerations acting for the card suit and the card value. And in this little slideshow here, I give you some of the code that might make up the playing card or the enumerations or the deck class with its properties and constructor that helps create the deck of 52 cards, as well as some methods to draw a card or to shuffle. And then once we have some of these classes, we could wind up using the deck of cards to maybe create a game of Go Fish with some other classes, like for a player and for something that's actually running the game. Or we could go and create it for another game, like the Game of War, which is another card game. And implement those kinds of things. And the interesting thing to note is that as we start building programs that become a little bit bigger, a little bit more useful, we're starting to encounter ideas or concepts about what the program is about. So with a game, I might have a die, and I would have cards, and I would have a player, and I might have some game rules. And notice as I'm talking about these different kinds of things, I'm really talking about complex data types that wind up having properties and behaviors and that work together in a certain way. And I don't tend to describe it in terms of just these primitive ints and strings and all this sort of stuff. A lot of those primitive types kind of get buried a little bit under the hood, as it were, of the other concepts that I have in my computer program. So we're going to go through a whole bunch of different kinds of examples of these. And what I'm going to start giving you, beginning with next class, is I'm going to wind up giving you some homework that you're going to need to be able to look at before you come to class. So I'll give you this homework on Friday. And then you'll have to have completed that homework before the Monday, because I'm going to have you create a lot of code at home in your own repository inside of your workbook. And then we'll use some of our class time to discuss these things, explain the different parts of it, all of that, so that you can have a better understanding. By the way, no, before Monday's class, yeah. So that'll be close to the end of Monday. By 5 o'clock on Monday. I'll give you until 5 o'clock on Monday to be working on stuff. One of the questions, that public fraction reciprocal, that's a good question. Let's go back to this. Let me go back to that fraction class where I had that. There it is. So how would I know what this fraction reciprocal is? What I would do is I would look at the grammar. So I've got the access modifier. I've got a data type. So this part right here is the data type. Okay. And then this part here is the name of something. So that's a name. And then what do I have right after the name? I have a pair of curly braces and I have a getter. So that must mean by virtue of this kind of grammar that I'm seeing right there, that's implying that this whole thing here is a property. So this is a property of the class. So the grammar tells you what those things are. That's why I was spending such a good amount of time going over that in the last class. So being able to see the grammar under the hood gives you a better idea of what it is that you're coding. I'm going to give you one more resource here before we go for tonight's class. And what I want to give you as that resource, it's actually part of this kind of documentation stuff, but it's this part here, the simplified C# grammar. So this is a good reference for the C# grammar that we're going to wind up seeing in a lot of this class. First of all, I just want to ask the general question in the chat. I'd like you to give me a thumbs up if you have heard of enumerations in C#. How many of you guys have heard of the idea of an enumeration? So I've got one person. Couple people. Okay, so only the term, but not really the idea. So like, yeah, so maybe it's really fuzzy. Yeah, you know, because somebody threw it out there once, but you're wondering like, what is it? What would we even want to use it for? All that sort of stuff. So that's what I want to cover in this particular presentation here. So let me start with the question, what is an enumeration? You can think of an enumeration as basically being a programmer-defined primitive data type. I've mentioned before that when we create a class, we're designing and creating new data types, and they're complex data types because they can have, let's say, many properties and they can have different sorts of methods and all that sort of stuff. So a class is a complex data type that we can define as programmers. Every class is a new data type. With enumerations, we can define those as well, but they operate as a primitive data type. So primitive meaning in a simplistic kind of a form. And you can also think of an enumeration as being a collection of named values, because ultimately an enumeration as a primitive data type is a value type. It winds up becoming something that has a set of well-defined or narrowly defined possible values. Believe it or not, you actually have been using something that's kind of like an enumeration, and it's built into the C# programming language as one of its built-in data types. Think about the data type bool, the Boolean data type. Remember, I said early on that that was the idea, a conceptual idea, that you can think of your Boolean data type as being like a check mark, yes, or an X, no, or true or false. It's not text, it's not a number, it's more of a concept kind of a thing. And with that Boolean data type, you have a narrow set of named values that you can assign to a Boolean variable, basically true and false. With an enumeration, we can define our own conceptual data types as a bunch of named values. And they were basically brought in because they are a better substitute for something that's been known as magic numbers. So to appreciate a bit about enumerations, we're going to have to go back in history to the land before enum. Way back when we were programming things, if we wanted to represent some conceptual kind of a value, we would sometimes just use an integer because we wanted to keep these different values distinct from each other. We would maybe just use an integer, and we would say, well, the number 5 will mean this, and the number 2 will mean this, and the number 3 will mean this, and we would sort of like just define as programmers in our head different meanings for each one of these numeric values that we would store in a variable. And that's essentially how we wound up keeping track of things. I was just looking the other night at a old bit of code for something called Super Star Trek. It came out in the late 70s, and I remember as a kid in the late 70s getting a book of computer programs, and in this book was this program for Super Star Trek, and we would type in all this code in our TRS-80 computer that we borrowed from the school for the spring break week, and my friend and I would type the game in, and we would store it on a cassette tape, and all that fine sort of stuff. We had magic numbers all over the place to represent all sorts of different kinds of things: status of the engines, status of the weapons, all that sort of stuff. And it worked. And it gave us a bit of functionality. We wanted to distinguish different states of some piece of information. And we would typically go and use that when the number of different states is more than 3. So weapons might be online, damaged, or destroyed, something like that. Otherwise, if it was only 2 different states, we could have used a Boolean. That would have worked fine for that. But if we had 3 or more states, then we wound up using these magic numbers. And it was basically simple integer values that we used to distinguish between each other. So the meaning of the integer value was basically only known to us as programmers. So what was the intent of the value? That was kind of hard to know as you were working with the code. So what we started to do to help us manage it a little bit better is we started to introduce constants. And we created these constants, and we said, okay, just so that our code will read a little bit better, what we'll do is we'll make a const int not started and a const int started, and blah, 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 and const int finished. So that would be a set of constants. And then we would go and check if we need to do an if statement, if status equal started, then we would know what that was and we could do our logic. But if we needed statuses for a bunch of different things, it could get a little bit more complicated. So if we had something that wasn't, if we needed to track something, a different kind of a concept besides, let's say, ship status, and we were instead looking at some other kind of concept we wanted to keep distinct, we were stuck with using ints, and you couldn't tell the difference between which ones were being used because they were all ints, they were all integers. So magic numbers were an imperfect solution. It left us with a bunch of questions. How do you share constants among classes and objects? How do you stop the explosion of simple constants that you could have all over the place? How would we group the constants to distinguish them from each other, aside from maybe just throwing a prefix on the name of it, which never gave you any compile time distinction? You just had to always remember the distinction in that regard. Or how do you limit or control the range of accepted values? So the magic numbers, they were imperfect. We could do stuff with them, but our programs could easily get buggy from using them. Well, enumerations offered a better approach. We can define a data type and say these are the possible values that there are inside of them. And that's exactly what enumerations do. We define a primitive data type, such as the return state, and we say the only possible values for return state can be no damage, minor damage, or significant damage. And that enumerated data type is completely different from the repair status, which would have the data types of not started, maybe some other things, and then finally finished. So enumerations would allow us to use these meaningful names that we started to get out of constants with our magic number approach. So we could use meaningful names for the values. And all of the stuff that's in the curly braces, those are the possible values. They're mutually exclusive in this particular case. So they allowed us to use meaningful names. We could clearly distinguish the values. The return state dot no damage is different from return state dot minor damage. And that basically allowed us to group all those values together. We can't cross-contaminate the enumeration values. If I tried to say return state dot started, it'd be a compiler error, and I would know that right away. I wouldn't have to try to figure it out at runtime and do a bunch of debugging. Under the hood, an enumeration still uses integers, still uses numbers, but it hides that blurriness that can happen and gives us this nice compile type safe way to work with conceptual ideas. So what are the parts of an enumeration? So in this example where I'm saying public enum return state, open curly brace, no damage, comma, minor damage, comma, significant damage, closing curly brace. Return state is the new data type I'm defining. No damage, minor damage, and significant damage are distinct values. They're different from each other. And because I have a data type and a value, I can now declare a variable. So if I had a statement that said return state shipment item is equal to return state dot no damage, shipment item would be a value whose data type is return state, and its initial shipment item would be a variable of type return state with an initial value of no damage. So three concepts that play closely together: variables, values, and data types. They play off of each other, they work together, but they are different things. They are different things. And they kind of coexist as we're in the stuff we're doing with our code. Because a variable is of a particular data type holding a particular value. That's how they work together. So what's happening under the hood of an enumeration? Well, by default, enumerations are integer-based values under the hood. So if we take another look at that public enum return state, where I've got in the curly braces a comma-separated list of constants, that you can think of no damage, minor damage, and significant damage as each of those being a constant. Under the hood, they are integers, and it starts numbering them automatically for us by 0, and then it increments each one after that by 1. So under the hood, return state dot minor damage would be equal to the value 1. Return state dot significant damage would be equal to the value 2. And that's the basics of how an enumeration works. Now we can do more with that. In terms of controlling the underlying value, we can say we want to have a different whole number data type. Integer is the one that it is by default, but we can say our enumerated value is a different data type. We could say it's a short if we wanted. If we wanted to do some stuff that we knew it would save a little bit of memory. It wouldn't be saving a whole lot in this case, but if you're writing a computer program that is basically going to be installed on your ring, have you ever thought of that? Have you ever thought of having a computer program that you install onto your ring? That'd be something wild. You've probably already heard of the idea of having computer programs in your watch. Memory space would be a little tight there, might be a little tighter in your ring, something like that. Um, but you can go and decide that that you want your enumerated data type to be based upon a short instead of an int, or long if you were going to have a lot of different ones you wanted to control that. But the long is a little crazy. I've never seen anybody really use a long for that. Most people just use the default int, but you can base it off of any other whole number data type. So those are my int, short, and long. And when you start out your enumeration, it starts out at 0 by default, but you can start it out at a different number. So here, for the day of the week, I've decided to start out unknown as -1, and then Sunday as the first day of the week would be 0, Monday 1, Tuesday 2, all the way up to Saturday 6. Starting off at 0 for Sunday is kind of useful if you're wanting to use it as an offset of the day of the week. You can add the underlying values if you wanted to do that sort of a thing. But typically we want to just stick. Usually we want to stick with the meaningful names rather than work with the underlying values. But that is there for us if we wanted to do that. Now, again, thinking back to the old days in which I was coding, back when having a 32K computer was thought of as, you lucky guy, you got a 32K computer off of your VIC-20. Or I got my Commodore 64 and I was thrilled because 64 kilobytes. Wow, the things you could do with that stuff. It's an amazing machine. Well, you may want to go and turn around and use an enumeration as a flag. So instead of using the whole integer as one distinct value, you may want to fine tune it down to the level of the bits, those ones and zeros inside. And so you can use enumerations as flags. One of the nice things about that is that you can combine different values when you use it as a flag. So I could have an enumeration called weapon status, where there are different kinds of states that it can be in. It can be offline, it can be online and armed, it can be online and firing, it can be online and damaged. So I could create my variable weapon status torpedo, and it is armed and online. So I'm doing a bitwise OR operation right here. I'm combining armed with online. So in the binary, this is 1, and 2 for armed, 1 for online. So the underlying value for the torpedo would be a 3. And it would be the combination of those two. And I could do in an if statement, if torpedo has flag online, then go ahead and do some stuff. So that's some of the cool stuff you could wind up doing with enumerations as flags. The other thing is that enumerations work really nice in switch statements. So if you had a nice simple little switch statement, switch status, if it's the case that it's the return state no damage, I'll do this. If it's the return state minor damage, I'll do this. Return state significant damage, I'll do that. So suddenly you might start seeing a whole lot of usefulness out of this concept called an enumeration. Well, when would you want to use enumerations? Basically, that's whenever you want to distinguish between simple statements. So there's simple states, and all you need is a custom primitive type to work in some conceptual manner for the purposes of your program. Just like the days of the week or months of the year or something like that to tell them apart. You'll want to use an enumeration if with your conceptual values that you want to work with, you have 3 or more distinct states. If all you have is 2 states, consider using a Boolean and then maybe prefixing it with like a word is. So you could say bool is available, and then true would be yes, it's available. False would mean no, it's not. So that becomes a little bit easier there. But if you got 3 or more distinct states, an enumeration might be a handy thing for you to use. Or if you have 3 or more overlapping states, in which case you can start using flags. And also if there's no intrinsic behavior to the state. So notice that one of the things about all of these is that we don't really do any thing with it that's number-ish with it. We don't add or multiply enumerations like we might add or multiply or divide integers. Right? Integers are meant for those kinds of mathematical operations. For enumerations, all we're interested in is distinguishing between them. We don't have to add them. We don't have to have them do anything special for us. So that's a really good set of situations in which you might want to lean upon this thing called an enumeration. And in the starter packs that I'm giving you, you're going to see some enumerations come into play. Some of you might have even started to get going in the E to M one, but that's basically how that works. Now we are back from the break with my screen material actually showing up. So we're going to take a little look at inheritance and composition. And inheritance happens all over the place in our applications. Whenever we go and create a class, by definition, every class that we create is going to inherit by default from object if I don't specify what the base class is. So if I have a class public class person with whatever in the body, by default, it's going to be inheriting from the class called object, getting all of that functionality that's designed in that particular class as part of the functionality that the person class will have as well. So that whole characteristic of inheritance is a key part of it. So that is correct. The base class is the object. So in terms of looking at the terminology for this, I would basically be saying that object is the base class, and I would be saying that put that right here. Person is the derived class. Now, there's some other terms that are sometimes used. The derived class is also known as the subclass, and the base class is also known as the superclass. So that's just some other terminology about it. But the notion that we have with inheritance is that When the person class, in this example, inherits from the object class, the person class will get or have all of the properties, fields, and methods of the base class for free without having to recode those items. So I'm not sure if you guys have heard of something called the dry principle. So the dry principle basically stands for don't repeat yourself. Let me say that again. The dry principle stands for don't repeat yourself. And the idea there is that we don't want to write duplicate code all over the place. And inheritance gives us the ability to gain functionality from our base class without the effort. And they called it inheritance because that's kind of the way it is in the real world as well. When you go, when you're growing up at home, you go to the fridge to get some food, and there's food there. You know, nice thing. Hey, there's food there. So you get a chance to eat that food. You didn't do anything to get the food. You didn't buy the food and put it in the fridge. You didn't even buy the fridge. You benefited from inheriting without having had to put any effort in for yourself. And that can be a powerful way to create more complex data types. As we create more complex data types, we build in more kinds of functionality in our application. But inheritance isn't necessarily the best way to go all the times. In fact, most of the time, what we want to have is we want to have composition. And composition is basically the whole idea that our data types, in other words, our classes or whatever we're making, can have members. So you can think of those as being, again, our fields or our properties that are complex data types themselves. So to say that we're using composition, we're saying that our data type is composed of other data types. And we can think of that in terms of, well, let's use the example of a car. If I had a class called car, car would not inherit from an engine. A car would have an engine. And a car would have wheels, and it would have a speedometer, but it doesn't inherit from it. There's a little bit of a rule of thumb in terms of knowing whether you're supposed to be using the inheritance approach versus the composition approach by generally going and thinking about it in this terms. Inheritance describes an is a relationship between the data types. If I go back to a particular data type idea that I talked about in an earlier class, I talked about the data type of a tree, if we had a class called a tree. If we had a more specific kind of a tree, such as an evergreen, we would say that the evergreen inherits from tree because an evergreen is a tree. So that's a good example of inheritance. On the flip side, when we're going and talking about composition, composition describes has a relationship between the data types. In that regard, I would say that a car has an engine. So your class car would have a property in there called engine. Or if you're thinking again to that other thing we were talking about a little bit ago, a train has an engine and a train has a bunch of rail cars. So that's the general big picture view of things. Now I realize you guys probably never got anything about inheritance in your programming fundamentals, but it is there in the background. It's always there, and but we're going to wind up thinking more times than not in terms of composition. And we've seen some composition, but we need to take a little bit closer look at inheritance. So inheritance represents the is-a relationship between data types. And that happens when we're going from a general data type to a more specific data type. Again, think the general data type tree, the more specific type of evergreen tree. And that's really useful when there is a common base for various types. So we have evergreen trees and we have the coniferous trees, if I've said that word correctly. So that tree becomes possibly a good common base for our various data types. We will use a base class when we're interested in having some common implementation that we want to have shared. Now, where are the places that we wind up seeing something like that? Well, a good example would be when we're building a library. If we're building off of some kind of library where we're wanting to extend the capabilities of the things that are in the library, we might use a little bit of inheritance there. By the way, in terms of object-oriented programming principles, there's something called the solid principles, where the S, O, L, I, and D of solid all refer to different distinct principles in some good object-oriented design. One of those principles is something called the open-close principles. That's the O in the solid. And if we have a situation where we have a common implementation we want shared, extending it by doing inheritance is one of the ways of accomplishing that. So here's an example. We could turn around and say that a car is a passenger vehicle. So it would inherit some of the characteristics of a passenger vehicle. On the other hand, our composition represents the has-a relationship between the data types. And our complex types that we make are more typically made up of other types. So by way of example, I could turn around and say a car has an engine. Let's look at some code that illustrates these points. Here we have a base class that we're going to use for inheritance. And I've called this class passenger vehicle. I'll get to that keyword abstract just before the class in a moment. Right now, I want you to draw your attention a little bit closer to the properties and the methods that I have in this class. My passenger vehicle has a maximum occupancy, the number of people that can be in that vehicle. And here I'm thinking maybe passengers only. I'm going to exclude the driver. So it's going to have a maximum occupancy. It's also going to have a current occupancy, how many people are in the vehicle besides the driver. What we can do with the passenger vehicle is we can add passengers and we can unload all those passengers. So those are some aspects of common behavior and description, as it were, that we'll want to be using in some of the subclasses we're going to be making. One brief little comment about that keyword abstract is that our abstract keyword prevents us from actually instantiating the class. So this abstract class, that abstract keyword, means we cannot create a new instance of this class. We would be constrained to only create instances of the derived classes. And the reason that we sometimes see our base classes as being abstract is because they represent such a general type that it's kind of incomplete until we get down into more specific types. So we don't always have an abstract class as our base type, but sometimes we do. And when we do have an abstract class as the base type, that means we're not going to be able to go and type out something like new passenger vehicle. That's just simply not going to be allowed at all. What's the point of such a class? We're going to be getting to that in a bit. Now, I made this one as an abstract class in part because I wanted to add in a couple of other things in my class. I wanted to add a couple of abstract methods. What I'm doing here with the public abstract void start and the public abstract void stop is I'm declaring some method signatures. I'm saying that I can start or stop my passenger vehicle, but I'm not saying how it starts or how it stops. With an abstract member of a class, the derived classes must implement those abstract methods. So, going back to some commentary, any class that inherits from the passenger vehicle will automatically get the properties methods of the previous page So those ones that I've shown. But that class must implement the abstract members of the passenger vehicle class. In other words, if I make a class that inherits from passenger vehicle, the subclass, that derived class that's inheriting from it, the subclass must supply the body of the start and stop methods to say how that vehicle starts and how that vehicle stops. Let's take a look at an example of inheriting from passenger vehicle. We can have a public class car. It inherits from passenger vehicle. So our car does not have to write the code to load or unload passengers. And the car also does not have to write the code representing the maximum occupancy or the current occupancy of the car. Now I've snuck in a little bit of composition here because I've created another class called motor because a car has a motor as its engine. So I added in an extra property there. So the car is a little bit more complex or more specific than the general type of passenger vehicle. But I might have another class that would inherit from passenger vehicle. And by the way, the car would start or stop. Whenever the car starts or stops, it's probably going to do something with the engine. But I might have another kind of passenger vehicle called a rickshaw. A rickshaw doesn't have an engine. The driver is the engine, and they pull the rickshaw. Now, the rickshaw has a maximum occupancy, depending upon how strong the driver is and how big how many seats are in the rickshaw. And it'll have a current occupancy. And the rickshaw can load and unload passengers just like the car. We don't have to rewrite that code. We've saved on duplicate code here. But a rickshaw starts and stops somewhat differently than a car does. So that's in terms of designing the classes. Well, what about after we've designed the classes? We've created two classes, car and rickshaw. They both inherit from passenger vehicle. I'm not going to worry about exactly what they do in their start and stop methods. All I know is that they can start and they can stop. They can add passengers, they can unload passengers. One of the benefits of inheritance is that I can refer to the more specific types by the general type. So, oh, what did I just press? I pressed the wrong key. I created a new file by mistake. There we go. I was trying to press the key to get my drawing going. There we go. So I can refer to, with inheritance, I can refer to the specific data data type or the specific object by its more general data type. So another way of saying this is that I can go and create a passenger vehicle that I might go and call a taxi. That's going to be instantiated as a new car. So what I've got here is I've got the specific instance of the vehicle, but I am referring to this variable here by its general type. Refer to the object by its general type. What's the usefulness of this? If I have a method that needs or can do stuff with a passenger vehicle, I can send it any kind of a passenger vehicle, whether it be a car or a rickshaw or a transit train or a motorcycle. I can send that passenger vehicle into that method, pass it in, and because I know it's a passenger vehicle, I would be able to access all of those inherited items off the bat. I'd be able to check the maximum occupancy, the current occupancy. I'd be able to load and unload passengers. I'd even be able to tell that passenger vehicle to start or to stop, even though I didn't know under the hood how it would start or how it would stop. That's all being handled by the more specific instance. So it builds in a kind of a flexibility that can become really handy in certain situations in software development. Now, not all situations. Remember, I said we will tend to prefer composition over inheritance. We're going to use composition a whole lot more than we will use inheritance, but inheritance can be useful. Some of the places that you sometimes see inheritance in game programs is having some kind of tree-like structure or some kind of inheritance structure to do with the weapons. You can have a general class called weapon. Then you can have more specific classes like a sword or a knife or a bow or a frying pan or whatever. If a frying pan can be a weapon. I think it can. You have to just watch the right YouTube videos. Anyways, that's a little bit of what's going on here, what's possible here. So let's take a little bit of a look again at some more code. Thinking about that taxi once more, consider this. I can have a passenger vehicle called taxi, which I can instantiate as a car. And then I can go with that taxi and I can add passengers. So let's say I add 2 passengers. And let's say a bunch of other code happens. Maybe stuff gets passed around into different methods, whatever comes back. But let's say I hit a point in my journey where the taxi can't go any farther. So it's time to switch the vehicles. I could create a different passenger vehicle called a tourist cart, which is a rickshaw. And I can unload the passengers from the taxi and add them to the tourist cart. So if you remember from part of the signature that I had for the passenger vehicle, when I unloaded passengers, it would go and the unload passengers method would return an int. And that integer value winds up getting passed into the add passengers so that the passengers that were in the taxi get added to the tourist cart, and then the tourist cart can travel on and do stuff. So that's a pretty powerful kind of a system. Now, you might be wondering, are we going to see situations where inheritance is going on? Yes. In fact, more often than not, you'll be using systems that have inheritance more than you'll be building systems that use inheritance. One of the things we're going to be doing in this course is we're going to be interacting with a database. And if you've taken or are taking database fundamentals, you will learn that there are all different kinds of database providers. You have Microsoft SQL Server databases. You can have Oracle databases. Some of you might have heard of something called Firebase, or you might even have something such as an Excel worksheet that is being used as a database. There can be all sorts of different databases. And what you're going to wind up seeing is us using a library of code. So again, think back to when we brought in the humanizer library. There's a whole bunch of code somebody else wrote. We'll bring that in with a NuGet package. We're going to use a library called Entity Framework Core that does all of the heavy lifting for us in working with a database, giving us a simple set of things we can do to build upon that library in order to work with our specific database. What we're going to be doing is we're going to be creating a class that will inherit from another class in the Entity Framework Core library called DB Context. Now, you don't have to worry about all the details of how the DB context works on the inside. What you do need to know is that you didn't have to write that code yourself, but you get to use it. And then just add in those things that are specific to working with your particular database. And that means of inheritance is what allows us to build more and more complex applications without having to start everything from scratch. We don't have to reinvent the wheel. So when we inherit from our DB context class, it's going to provide the basic functionality for working with databases. We simply write out that we're inheriting from the DB context and provide the specifics of our database in our class, and we're good to go. In the same way that we could have gone and created our car class, and we didn't need to know or worry about the details of how or what happened with adding and unloading passengers. All we had to do is provide our own specifics about how we started or how we stopped. Or some other stuff which I haven't shown in this slideshow. Maybe the base class will have some abstract methods or virtual methods, I should say, that we could override, just like we did an override of toString for the object class. What this opens up for us is a whole world of possibilities in terms of how we can code things. Let's go and give a little bit of a start to our look at arrays. Grab my little presenter window and make that go full screen. So at least half of you guys, a little bit more than half of you guys have said that you've learned a little bit about arrays in programming fundamentals. When you ask the question of what an array is, basically you should recognize that an array is a series of distinct values that we refer to as elements in the array. So there's multiple values that you can have in an array, and they're distinct from each other in the sense that that the values are stored separately. More specifically, when we think of an array, all of the elements in the array, all of the items in the array are stored one after the other. We basically refer to that as being stored contiguously in memory. So contiguously means one right after the other. And when you think of an element is basically an individual item in the array, and you find or distinguish that particular element in the array by combining the name of the array with an index or subscript. So for example, if you had an array called array name, you would say array name square bracket index closing square bracket in C# to refer to a particular item in that array. It's good to remember that an index or subscript is essentially an integer that we use to indicate the position of that element in the array. Does anybody remember what the smallest or the first index position is? Anybody answer that inside the chat? Yeah, that's right. You got it. So the first index position is 0. Did anybody tell you why it is 0? Did anybody explain to you why? Not sure if they did. If it's the entry point 0 to 9. Okay, if for 10 numbers it'd be 0 to 9. So there's actually a mathematical reason why, and it does come up in part to the notion of the fact that an array is a reference type. So we'll talk about that as well. But we'll take a look and see why is it that we have an index position of 0 as the first item in the array. So more looking at the question of what is an array, when we think of the physical size of an array, what we're referring to is the number of elements that are in the array. It's actually possible to create an array of 0 elements. It's not very useful, but it is possible. You can have an array of 0 elements. And you can have as many entries in the array as basically the maximum value for an integer. And when we think about the physical array, we need to also make note of a concept referred to as the logical size of an array. Because if you have an array that is only partially being used, that is, other parts of the array are considered to be quote unquote empty, even though in truth they're not really empty, but they remain unused, would probably be a better way of referring to it. The logical size of the array would refer to the number of elements that are actually being used, and the logical size cannot be less than 0. And the maximum value is basically the number of elements in the array. Now, when you declare an array, the size of the array is fixed. And when you declare an array, you're basically saying to the computer to set aside memory for it. So the memory allocated for an array in terms of how much memory does the computer need to set aside for an array is going to be dependent on the size of each element and the number of elements that there are. So if you're using, for example, an array of integers, and you know that an int is 4 bytes, and you had 10 elements in that array of integers, you would have 10 times 4 or 40 bytes of memory that's set aside for that array. So let's take a little bit of a look at this visually. In our memory, we might have a particular array. So the name of the array is basically referring to the address point for the array. And the first index is at 0 for the first element. The second element, index 1, third element, index 2, all the way up to the last element, element n, whose index position is actually n minus 1. Because we're starting at 0, it goes to there. Now, as you think about the array, it's good to remember that an array is a reference type. And right away, when I say that an array is a reference type, you should be starting to get some of those pictures in your mind of what I showed you before about basically having 2 boxes. When we say it's a reference type, we're saying that the array refers to a memory address where the values are actually stored. We also have the understanding that every element in the array is of the same data type. So we know that the size of each element in terms of bytes is going to be fixed. And what happens is, to find the memory location of an element in the array, we do a calculation. We basically take the starting address plus the element size and index offset. So let me go and add a little bit of extra drawing onto this. In truth, when we go and declare, get a box instead of a line, when we go to declare our array, so we have our array name, what winds up happening is that we have a value inside 0x0CA20C00. So the array is essentially pointing to where that first element is. So you take that memory address, so that really is the address of the very first element begins right at that spot. That's where that first element is. And then to jump to a particular element, you're doing your calculation of the element size times the index offset. So if each element's size is, as I was saying before, 4 bytes, and you're looking at index position 0, so you're looking at index position 0, 4 times 0 is 0, which means it's 0 bytes from the start of this address. So that address plus 0. That's how you get to the first one. And that's why it is set at 0, basically just to make the math easier for the computer. If you wanted to get to the fourth element, you would multiply by its index position of 3, and knowing that, again, if each element size is 4 bytes, you would be offsetting by about 12 bytes from the beginning of the array. That's the whole idea behind why it's zero based. Now, when you were introduced to arrays, I imagine you focused primarily on one-dimensional arrays. Let me just ask a question in the chat of you guys. Thumbs up if you were shown about two-dimensional arrays. Yeah, the whole array has one address which is the starting position of the array. As a reference type, that array name is the starting address of the array. And everything else about finding a particular item in the array is done by math. A couple of you guys had seen some two-dimensional arrays. Okay. Now there's a lot of ways you can set up arrays. You guys have seen the one-dimensional. Oh, you were just told about two-dimensional arrays. Okay. Well, with a two-dimensional array, the math would be, you'd still be doing math, but you'd be doing math across 2 dimensions rather than just the what shall we say? Rather than just across that 1 dimension. But there are quite a few different kinds of arrays. There are such things such as one-dimensional arrays, of course, two-dimensional arrays, and three-dimensional arrays, which I call multi-dimensional arrays down a little bit later. You can have 2 separate arrays that are totally physically separated, but you're purposefully programming them so that they're the same size and so that the information in one array relates to the information in the other array at the same index position. We call those corresponding arrays. But there are also multifunctional arrays, multidimensional arrays, multifunctional, multidimensional arrays, jagged arrays, arrays where the index has a meaning, and we could probably go on to a few other kinds of things I'm not even mentioning here. So arrays were powerful because they gave us the ability to refer to several values by one variable name. And the whole idea for that was that with that one variable name, just call that array name once more, array name. With that one name and some indexes or subscripts, we could refer to individual pieces in this. The only way that it works is because each element is stored one right after the other in memory. That's why I said arrays are contiguous. The values are one right after the other. And the individual values are referred to by their combination of your array name and your subscript. That was part of the the power of it, was giving us all these different sorts of values. Now, when you did arrays, you wound up doing arrays of all your primitive types, but you can have an array of objects as well. And that can give quite a lot of functionality and flexibility right there. Now, arrays are not a perfect solution, but they were the first kind of solution that made sense in terms of the evolution and development of computer programming. There are other ways we can refer to a collection of items in things such as a linked list, which is the kind of mechanism that you can imagine behind the scenes of that list of T, and other kinds of collection structures such as stacks and queues. But the arrays tends to be the first place where you get learning about having a single variable name to refer to a whole bunch of pieces of data. Now, with arrays, you wind up learning some different array processing. You will learn about how to do a sequential access for an array. So you just do some loops and you start at the beginning of the array and you go all the way up to the end. If you go outside the boundaries of an array, then you wind up getting an argument out of range, or exception being thrown if you try to access some memory outside the boundaries of the array. Array processing, you can also do it in a non-sequential access. One of the common ways of doing a non-sequential kind of access in an array might be if you are searching an array that happens to be already sorted. And you can do something called a binary search, which is a very fast kind of search for sorted arrays. Or you can just do random access. And random not in the sense that you're just totally going random, as in you don't care about which one you land at, but in the sense where you're trying to do something meaningful with how you're choosing your index value. Now, we process arrays for various reasons. The first, of course, is to initialize an array with a bunch of values or load up a bunch of values into an array. It might be for modifying particular items in the array or searching. You might use an array for doing things called aggregation. If you took database fundamentals, you might have been learning about aggregations, such as the getting the total or the average, or counting, or getting the minimum or the maximum. All of those are ideas of aggregating. There's also the notion of sorting. If your array is not sorted, you may want to put it in a particular sort order, and there's all sorts of different algorithms you can choose for doing that. And of course, with an array, you may also want to insert or remove items in the array. But again, for your array to be useful, your information really needs to be stored contiguously, one after the other. So if you're only using one part of an array, thinking back to this thing here, if you're using only one part or only part of the array, and you decide you want to do an insert or a delete, well, doing a delete of, let's say we want to delete the third element. If I wanted to get rid of the third element, I wouldn't want to leave a gap there. I would have to make sure that I have gone and pulled each item up so that there's no gap. And I'd have to go all the way through. If you start leaving gaps in your array, then you make it really difficult to work with any of the data inside of that. Similarly, if you wanted to go and insert a new item into the array at a particular point, then you would need to go and bump all the items down in order to do that. And of course, in terms of bumping it down, you'd have to start at the bottom and pull them down until you have an open spot that you can put that in. Again, all without violating the size of the array. So a little bit of curiosity there. In CPSC 1012, give me a thumbs up if they taught you to insert items into an array and track the logical size of the array. Did they go over any of that? And I'll do another little bit of a question of thumbs up if they taught you to delete or remove items from an array. Okay, so a few of you are indicating that they did. Yeah, kind of like read, write, delete as in the sense of remove or replace. Now, and you're starting to think about StreamWriter. Okay. Yeah, you guys would have spent some time on StreamWriter. You're going to learn some things from me about file input output that will make you want to contact your programming fundamentals instructor. The the thing that you would have seen if you had to go and insert items into an array, into the middle of an array, or remove items from an array, is that you had to really be careful to make sure that you didn't leave any gaps, that you didn't overwrite any information. You were responsible for quite a lot of pieces, as well as making sure that you don't exceed the size of the array, because once your array is filled up, you can't put any more items inside of it. If you wanted to have more items inside of an array that's completely full, the only solution is to recreate a new array that is physically bigger, copy everything over, and then you've got room to insert new items. And yes, you're exactly right. Lists and dictionaries, for those of you that might have seen dictionaries, but lists are a whole lot easier to work with, because a list, for the first part, is something that can easily grow or shrink to whatever items you have inside. And you never really have any quote unquote empty items inside of a list, because it's managing its size according to how you're adding into the list or removing items from the list. And it just makes things so much nicer, so much cooler. And dictionaries are related a bit upon them as well. Under the hood, a list is typically thought of as something like a linked list, that kind of an idea. So you can have, when we used to teach some stuff on algorithms quite a number of years ago, we would teach about doing a singly linked list and a doubly linked list, and learning how those worked. Well, if you got about this much stuff that I've shown you here, then essentially you got the basics of working with arrays, and you're probably pretty good just stopping at that point. If you wanted to learn a little bit more stuff about working with arrays, I do have some additional things. There is some look at different approaches to sorting. I'm kind of curious. Thumbs up if you were shown the bubble sort in 1012. Don't know if anybody showed you the bubble sort, how to sort an array. Bubble sort is probably one of the slowest sorts that there are. And in practical usage, you would never use a bubble sort. If you had a list of names and phone numbers for everybody in the Edmonton and area, which is basically about 1 million people, and you try to sort that thing by using a bubble sort, that would take you weeks for that bubble sort to run, even on modern computers. Instead, the quick sort or the radix sort wind up being a whole lot faster. Radix sort is actually insane in how quick it is. You can see some of those links of the various sorts and some animations about how they work following those links. I'll give you, by the way, I'll share the link for this whole slideshow after a bit here. One of the important things in the whole process of working with a sorting kind of algorithm is that you need to do some swapping. It's a core part of most sorting algorithms. And that's where you basically take the values that were in two different locations or places in your array and switch them. And that typically involves having a third variable. So you go and you assign your first variable to that temporary variable, and then you can overwrite it, because as soon as you say your variable B is assigned into variable A, you lose the information that's in variable A. That's why you're storing it in a temporary variable, so that afterwards you can take that temporary variable and put it into B. So it always requires that third little piece of information. I've got a little bit more details on some of those things. If you want to find out about a selection sort and the essence of how it works and its pattern, you can check out this flow chart to try to see how you might go and implement a selection sort. This one does it in ascending order with a zero-based array. There's an insertion sort algorithm where, again, I've got a little bit of a flow chart you can use to see how an insertion sort would work. Of course, there's the bubble sort. I showed you a little bit of that diagram inside of that first practice starter kit when you were working with the accounts. Also have a little bit of a thing in terms of the math converting decimal to hexadecimal, a little bit of a thing on the quick sort, and at the heart of the quick sort, well, yeah, a little bit of just talking about the quick sort. After you're done sorting, then you wind up looking at doing things like binary searches. So I'm not going to go over all the details of all of this sort of stuff with arrays, but just to let you know that there is a whole lot more information in that slideshow if you're interested. Okay, interfaces. Whenever we talk about interfaces in computer programming and software, this becomes one of those terms that kind of gets used with different kinds of meanings. A lot of people, when you first talk about interfaces, they tend to think about the user interface, that is the screen or whatever that the person interacts with. But another big use of interfaces in languages like C# is where we talk about it as something that describes the signatures for properties or methods. And the reason for the use of the term interface, if you go back to the dictionary definition, where it means interact with another system, person, organization, etc., or in computing, connect with another computer or piece of equipment by an interface. The whole notion of an interface is that it is describing the way that you connect or interact with something, how you can go and use something. All of us have experienced interfaces even from the youngest ages. If you've ever seen a power outlet in your home, a place where you can plug in, let's say, your toaster or your computer or a hair dryer or a space heater or something like that, that plug-in follows a particular kind of a pattern and interface. It describes how you can interact with it to get your 120 volts of power into your device. And the interface is shaped differently for 240 volt, which you would use for your refrigerator or something like that. So the interface describes the way that you interact with something. Working with interfaces is a common kind of a thing in computer programming because it allows us to talk about the things that we're working with, the classes or the objects that we're working with, in terms of some common kind of functionality that might be handled differently by different kinds of objects. Here's an example of a simple little interface that I've created. I call this I adjust speed. So we have a public interface, I adjust speed, and it defines two methods and one property. The two methods, accelerate and decelerate, are void methods. They don't return anything. And they each take two parameters. One takes a double and the other or they take first a double followed by a time span. Notice that while this looks a lot like a method with that grammar, so you have the return type, the method name, and a parameter list, it doesn't have the curly braces for a body. It just ends with a semicolon. An interface typically just defines the method signature. So the method signature is all about the name of the method and the parameters being passed in. So this part here is the method signature. And I've got two methods in play. Now, I also have a property. So in terms of my property, this is the signature for my property, where I identify the data type of it and that it is a getter property for the current speed. With this kind of interface, I can apply it to various kinds of classes. I can write a class that implements this interface, and that implementing class would describe how those methods work. So a class can implement an interface. When it does, it will or should define the body of the methods or properties in the interface. So that goes and that class you create defines here's what's going to happen when we accelerate. Here's what's going to happen when we decelerate. One little bit of a note. It used to be that an interface could not define the body, but as of C#, it's either C#8 or C#9, I can't remember. An interface can describe a default body for the methods, for the method that you would have for that interface. So that's kind of a new thing. I tend not to do that much because if I'm going to have a default body, a lot of times I tend more towards maybe just having an abstract class or something like that. There's pluses and minuses to all of those. Well, let's take a little bit of a look at how I would go ahead and use the iAdjustSpeed. Here I've got a treadmill, public class treadmill. It implements the iAdjustSpeed. You can accelerate and decelerate a treadmill, and you can see what the current speed is. Notice that here I've got the bodies for the accelerate and the decelerate. Right now they just have comments in them, but I would put in whatever logic I would need for a treadmill to speed it up or slow it down. And as I speed it up and slow it down, I'd probably be modifying the current speed. I have a public get for the current speed, but the setter is private. When you think about the interface itself, notice that all the members of the interface do not have an access modifier, because the assumption is that if you implement this interface, you are making all of those members publicly available. So with my treadmill, my accelerate, my decelerate, and my current speed are all declared as public. And the treadmill would implement that iAdjustSpeed one way, whereas a car would implement the iAdjustSpeed in a different way. But it would follow the same or be sure to support the contract that's being established by the interface. An interface is something that effectively defines a promise of how or what it will do. Here's another example of a class that can implement iAdjustSpeed. You can have an elevator that implements that, where you can accelerate and decelerate the elevator, and it would have a current speed. Now, once you have various classes that implement interfaces, you have the ability to refer to the instances of those classes by that interface. In other words, by way of example here, I'll throw a little bit of C# code over top of this slide here. I could go and write something, I adjust speed device is equal to a new elevator with whatever parameters it might wind up needing. Or I could go later on and say that I want the device to be equal to a new treadmill. with whatever items I would pass into the constructor. But the key thing here is that I can refer to the concrete implementation by its general type. So this here, the new elevator, is a concrete implementation or instance of the interface or the general reference type that I'm using called iAdjustSpeed. That ability to refer to a more specific class or more specific object instance of a class by a more general data type is what allows us to create programs that go and use these things in various ways that give us flexibility. Consider now that we have an iAdjustSpeed that I wanted to have a control panel for something. So I can have a control panel that takes in some object that supports the iAdjustSpeed, and I would store that right here in a private field. Here's the constructor, brings in that object, and then maybe my control panel handles a key press. And depending upon the key that was pressed, maybe the W key, you would accelerate, let's say at a boost rate over a certain time span. So imagine then if you wanted to use this, we'll just go to the gaming example where you wanted to create an asteroids game. You could have that iAdjustSpeed interface being implemented by both the asteroid pieces as well as by the spaceship that you would have in there, or the alien UFO that goes by. And you can have a control panel that gives manual override for that with pressing the W key to go up, the S key to decelerate, and you can put on other interfaces as well to turn and that sort of stuff. So hopefully you're starting to imagine a little bit about how this can work. Here's another quick little example. This is one that I've kind of adapted from an old text-based Star Trek game. We would when I was young, I basically was able to borrow one of the school computers and take home. This is like in late 70s, early 80s, and take the computer home and then enter in a bunch of computer games that I got out of a book, and Star Trek game was one of them. If I was doing it in a modern kind of a way, I might create an interface called iLocatable, which would mean that you would be able to get an item's quadrant position, sector position, and quadrant and sector numbers, or iPingable, where you can go and ping it. And then you might have something like a star that's an abstract locatable that implements iLocatable. And so you have a star, and then you maybe the abstract locatable also implements the iPingable, and then you can ping both of those things. Or in space, you can ping an area of space and get a certain string back. So the possibilities for working with interfaces is actually pretty large. Well, that's a little bit of a high level view of working with these things called interfaces.